your instructions. In general, you just need to follow the PowerPoint. On some of the slides, there are instructions for you in the yellow boxes. Please make sure the sound is turned up on your device so you can hear the narration. And remember, if a slide asks for homework, don't forget to send it in via Show My Homework. And if a slide asks for Educate to be completed, don't forget to do it by the date given.
In our last lesson, we looked at something called specific heat capacity. Now, this is the idea that different materials require different amounts of energy to raise their temperatures. And we use that idea to explain why we would choose certain materials to do certain jobs. By the end of this lesson, you should be able to apply an equation for specific heat capacity and calculate the specific heat capacity of different materials. In physics, we often talk about systems. Now, a system isn't anything complicated, it's just our word for whichever part of the world we happen to be studying at the time. So our system could be a metal block, or our system could be a volume of gas. When we're talking about specific heat capacity, if the temperature of a system changes, the increase in temperature depends on three things. First of all, how much material are you heating? So it depends on the mass of the substance heated. Two, it depends on what type of material it is. We know now that different materials have different specific heat capacities. That means they can absorb different amounts of heat before their temperature changes. Three, it depends on how much energy we put in. And it's also worth remembering that if we heat something, we're putting energy into that system, but later on, if that object cools down, it is releasing the same amount of energy back to the environment. Here are some pictures of some real-life materials. These are all metals. Now, firstly, there are different amounts of metals here, so different masses. Secondly, the materials themselves are different. We've got some aluminium, we've got some steel, we've got some brass, and we've got some copper. All of these metals have different specific heat capacities, so they change in temperature by a different amount, even if you put the same amount of energy into each. Now we can work out the specific heat capacity of a material by using an equation. And that equation reads like this. E equals mc delta theta. And when you write it down, it looks like this. So let's have a look at each term individually. First of all, E is the amount of energy that we put in, or the amount of energy that is released from the system, and energy is always measured in joules. The second term, M, stands for mass, and mass is always measured in kilograms. C stands for the specific heat capacity of that particular material, and each material has a different specific heat capacity. It's measured in joules per kilogram degree centigrade. The final term in our equation is delta theta. Now delta just means the change and theta is the temperature. So delta theta means the change in temperature. So for any given material, for a given temperature change, you can work out how much energy was put in by multiplying m times c times delta theta, the mass times the specific heat capacity times the change in temperature. So let's use the idea of specific heat capacity to answer some questions. So here we have some information in a table. Now the information relates to three different materials and it gives you their specific heat capacities. Question 1. Which substance requires the least amount of energy to raise its temperature? Well, we know from our previous work that materials with a high specific heat capacity can absorb a lot of energy for a very small temperature rise. So in this case, it says which substance requires the least amount of energy to raise its temperature, which means we're looking for a material with a low specific heat capacity. And the lowest one in the table is copper. Question number 2. This refers to the same table of information. How much energy is needed to increase the temperature of 1 kilogram of water by 10 degrees centigrade? So the first thing we need is to work out what the specific heat capacity of water is. And here it is given to us in the table. Then all we need to do is write down our equation. E equals mc delta theta. Then we can substitute in the figures that we know. So the mass is 1 kilogram. That's given to us in the question. The specific heat capacity is 4,180. That's given to us in the question. And the change in temperature is 10 degrees. That's given to us in the question as well. So E equals mc delta theta. Substitute the numbers in that we know, and out comes your answer, 41,800 joules. That's the amount of energy needed to increase the temperature of 1 kilogram of water by 10 degrees centigrade. Part 3. How much energy is needed to increase the temperature of 2 kilograms of copper by 20 degrees centigrade? So again, let's write our equation in. E equals mc delta theta. This time the mass is 2 kilograms. C, the specific heat capacity of copper, is given to you in the table, 390. And the temperature change this time is 20 degrees. So if you substitute all three of those figures in, you get an answer of 15,600 joules. So here's one for you to try. Water has a specific heat capacity of 4,200 joules per kilogram degree centigrade. How much energy is needed to heat 2 kilograms of water from 10 degrees to 100 degrees? Pause the recording here while you have a go at this question. Now let's work through it together. First of all, let's write our formula down. We know that E equals mc delta theta. So here's the equation in words, and here is what we know. We know in this case that m, the mass, is 2 kilograms. We're given C, the specific heat capacity of water in the question, it's 4,200. Now we don't know the temperature change, but we know it starts from 10 degrees and ends up at 100 degrees. So we can say the change in temperature, delta theta, is 100 minus 10 is 90 degrees centigrade. Now that we have all of these bits of information, we can write our equation again, and we can substitute in our figures, and the answer we get is 756,000 joules. Now it's your turn to try a couple of exam questions. They are on the attached PDF. Please can you send your answers to Mr. Rahman by Friday the 5th of June. Thank you.